All right, here's where I left off last time. Um, we were doing the periodicity of the elements, the word I couldn't come up with, and truly appreciate all your encouragement. A lot of these words, as you pointed out, I'm not 100% sure on how to pronounce. So I'm guessing, for some reason, I can't pull up the YouTube videos right now on my computer. I'm having to restart, but I'm just going to go ahead and move forward. I think you're wanting me to say Leibniz as opposed to Leibniz. And yeah, that's definitely a little twist of the tongue I'm going to have to be careful about. Also, I really have a hard time with Schrodinger. I'm not exactly sure on that guy either. And then I've even heard people say Max Planck. Planck. I've always heard Max Planck. So I hope I'm not fudging that one up. But basically, where the last video ended is this periodicity of the elements. And when you add up the 2 and the 8, you have 10. And then the 8 and the 2, you have 10. So this adds to 100, and obviously it's just missing the 20. And this shows how many elements. Kelvin is suggesting that there are only, and ever will be, only 120 stable elements, and they follow this periodicity. Hope I'm saying that right. Again, this is my week to really, I don't know, get going in a conversational tone. I've got all this stuff written down and thought out and organized in one shape or another. But in the end, this is really just a test run. We'll get a real test run here in the next week, probably next week, where I'll have some slides and obviously the c-squared circles, our time domain of 1 second measurements. That's all going to be explained. I'm going to have a section on the coordinate systems for sure, and why, what they represent as far as a seconds measurement or a second squared measurement, and how to differentiate that between the 2D mass energies and the 3D matter topologies. So that's where I left off on my notes last night. And obviously, I like the idea of the who, what, where, when, how. Where is it at? Who, what, where, when, how. Obviously, Kelvin C. Abraham, what? Geometric unification. What does that really mean? What does that really look like? Touches on that bottom-up approach that we've discussed before plenty of times. Where? So in this case, where did the physical constants come from? In this case, where, like, some of these are in the what category. Here's where I'm confused. What? A geometric unification. What? Is energy really quantized? Like what? Yes, Tetryonics fully supports the idea of a finite building block of mass energy. And this is the quintessential goal of Max Planck. Max Planck. I don't know. Tell me which is better, which is correct. I'd love your input. Um, so, what is charge? Where are we stuck in our understanding of physics, and is there a way to get unstuck? I feel that this geometric approach definitely gives us a mechanism to get unstuck. So the win, obviously 2008, 2016. This is where and how long Kelvin has been working on this. Only in recent years, since about 2012, has he opened up the materials to a larger review from the general public and people like me who are just endlessly fascinated and curious with this approach. How does it differ? These are all things I'm going to address in the conference, slideshow style. So nothing too crazy, nothing too spectacular before we actually get into physics as geometry, and one cannot be separated from the other. As we all learned long ago, the famous saying of Plato, "Let no one ignorant of geometry enter." Now for a more modern quote on the topic. Now this is going to be my quote of John Archibald Wheeler. That's where you see this jaw down here. Now I didn't write the full quote, but it goes something like this, and I know you've heard this before, but at the bottom of it all, or actually it starts differently. To my mind, at the bottom of it all is not an equation, but an utterly simple idea. And to me, when we find that idea, We will all think to ourselves, oh, how beautiful, how could it have been otherwise? I'm paraphrasing. His other quote that kind of wraps that whole concept up is the idea of surely a door will open and expose this central glittering mechanism of physics in all its glory. And then here's where I'd like to talk about Wayne Roberts, only because this is where I got my curiosities piqued. We've talked about Wayne Roberts over the years. In light of the so-called square numbers of physics, we have applied a square peg to an otherwise triangular number. So again, paraphrasing this quote, just giving you some highlights and how I'm going to be segueing from point A to point B. So let's see. I really don't know. Again, looking for input from anybody. Basically, it's you and Joe. Hi, Joe. Long time no hear. Hope everything's going great. But basically, I don't know if I should be saying anything about myself. I mean, I'm really just want to get in there and start talking about Tetryonics and leave the rest of it to the personal interactions that I'm going to be having at the conference. So, anyways, I've spent 3 years studying this in my spare time, and it's been very satisfying. And obviously, I have many more years ahead of me still. I have by no means exhausted my attempts at understanding Tetryonics and what it has to offer. This is just some other notes. I don't think. Well, I don't know. It's almost like all of humanity is just waiting for that next revolutionary idea. And what I mean by that is we're all just waiting for that new concept, a refreshingly simple concept, to help us along the way. It's kind of interesting. It's been such a long time since I've seen one of these ideas since the Tetrayonic materials. It feels to me that it's been a very long time. I'd just like to remind everybody, it feels like it's been a long time and that we're overdue for this type of revolutionary thinking. And in my opinion, I believe that Tetryonics is worthy of the attention of a great many minds. So basically, I'm here to pique your interest, and you're going to be able to go into the Tetryonic materials on your own, in your spare time, in your full time, whatever it takes. That's the only sacrifice we make with the Tetryonic materials is your time. So that's basically why we're here today. Share this info and give everybody a jump start where we think the future of physics is going. The concepts are simple themselves and based on the idea that energy is the equilateral geometry. So without getting too specific on this point, omega of Tetryonics, or the quantized angular momentum of Tetryonics, is really this squared meters per second. And this is buried under the symbol for Planck's constant. The units of Planck's constant are kilogram square meters per second. Okay, but what we really have is mass omega. So there's a couple ways of looking at this and it's showing this, but from a geometric perspective, we got mass omega as Planck's constant. This omega, we have to realize, actually is reflective of the equilateral geometry in the square meters per second. So obviously I'm going to have a lot of pictures on this. I'm going to go real slow through the odd numbers, adding up to square numbers, and how the linear momentum relationship runs up the apex of the triangle. Even before we really get into the E field and the magnetic dipole partitioning of each Planck quanta. So again, these are just some interesting thoughts. Moving on, things like this we've already talked about. This is kind of the Wayne Roberts idea. Side length of 3 areas, 3 squared relative units. Down the bottom we have this normal or bell curve distribution. Nothing new. Now, this is like a dot notation. This is kind of just different. Obviously we have square numbers here, but we've arranged them into a diamond shape. And then if you connect those dots and draw these lines, then you realize you have 18 h nu quanta, or you have 9 h frequency photons. So the easy way to count this is, sorry about the shadow on my finger, the easy way to count this is to look at the photon distribution. There's 1 right there, then right here there's 1 and there's 2, and then there's 1, 2, and 3, and there's 1 and 2, and then there's 1. That adds up to 9. So you can see that that's a 9 photon distribution. So I don't know how much more time I have here. Here we are at another 10 minutes. It's pretty easy to go on and on and on, and I have so many other points that I want to get